Okay, so um, we want to determine whether the following series converge or diverge. Let me give you a moment to copy down the examples here. Okay, so let's look at this first series here. Now, one thing you might think about when you look at this first series is, can I express it as a telescoping series? Well, to express the series as a telescoping series, you'd have to be able to factor the denominator. And I can tell you that denominator is not factorable. I mean, what I mean is you're not going to factor and have nice factors. Um, so the telescoping series approach would not work. It's not a geometric series. It's not a geometric series. That's for sure. Um, so uh, let me ask, in the denominator here, what power dominates in the denominator? For this series, n equals 1 to infinity of 5 over 2n squared plus 4n plus 3, what term is the dominating term as n gets large? That's right, Tyreek and John, thank you. The 2n squared. So essentially, you could sort of think of this, again, when we're trying to see if a series converges or diverges, what we care about is the eventual behavior of the series as n gets large. So if we were to sort of ignore the 4n and the 3, this series would actually behave, well, I want to be a little bit careful here. This series would actually, I got to be careful. Let me just see here. I want to make sure that everything I'm saying is correct here. One moment. I'm just writing something down. One moment. Yeah, this series will, in the end, I don't know if I want to say it like that. I tell you, I'm not gonna go down that path with this. I'm gonna just let the series as is. Okay. Not that the path's wrong, but I want to keep it simple. So this first series, what I want to do is, since I can't, since it's not a geometric series, since it's not a telescoping series, I have to basically think about, to establish if the series converges or diverges. One thing I could do is compare the series with the series I know something about. And this is the approach called a comparison test. So on that note, let's go to the solution here. It turns out that the terms of this series, which are 5 over 2n squared plus 4n plus 3, all the terms of the series are positive, by the way. All the terms of the series are positive. But the term of the series, I can say, is less than 5 over 2n squared. Okay, I can say that. I mean, it's just a simple inequality. Of course, 5 over 2n squared plus 4n plus 3 is less than 5 over 2n squared. Well, it turns out that if we were to consider the series where the terms of the series are 5 over 2n squared, and I'm doing that because of my inequality, naturally I can factor out the 5 halves so that the series becomes 5 halves times the sum of 1 over n squared. And the question is now, does the series, the infinite series, does this infinite series where n equals 1 to infinity of 1 over n squared, does that series converge or diverge? So you haven't seen this series before. It's your first time seeing that series. It's called a p-series. It's called a p-series, where p equals 2. Okay. Do you think that series converges or diverges if you had to use your intuition? Who thinks they can offer their instincts on that? And a little hint here, what if you had the improper integral What if you had this improper integral? That's a p integral with p equals 2. Does the improper integral converge or diverge? This improper integral. That converges. That's right, Tyreek. This means then that the series also converges. Okay, it means the series also converges. So the p-series, convergence or divergence of a p-series, acts the same way as the convergence or divergence of a p-integral. So the fact that we have then 5 halves, well, hold on here. Just make this a little bit lower. The series, this series here, converges because it's a multiple 5 halves times a convergent P series, where the P series is P equals 2. So anytime you have a multiple of, if the P series converges, that means the sum's finite. Well, if you take 5/2 times a finite sum, you're going to get a finite sum. So why was this useful? Why was this useful? Well, is our series that we're interested in bigger or smaller than this series here? Is the series that we're interested in bigger or smaller? That's correct. Good, Robin. Good, Tyreek. Our series is smaller by virtue of the fact that the terms of our series are smaller than the terms of this P series. And so this means then, by the comparison test, if the larger series converges, the smaller series has to converge. Okay, that's the comparison test. So what you have here, right, is you have, try to write it as nice as I can. Okay, you have kind of tough to write with this marker, but you sloppy. Make that nicer. Okay, get this off. So you have a series here. You have a series here. And I apologize. It's just hard to write with this. I'm using the mouse, to write, and it's just hard to write. But essentially, what you're doing is you're comparing. You're looking at. You're trying to determine whether this series converges or diverges. The series we're interested in. Well, the fact that our larger series converged, which means it has a finite sum, means that the smaller series has to converge also. We don't know what the sum is of the smaller series. We have to use a computer to figure that out, to get an approximation, but this is how the comparison test works. Okay, are there any questions on that? Who's comfortable? Who's comfortable with that? Maybe give me a thumbs up if you're okay with that. Thank you, Tyreek. Thank you, John. Thank you, Julia. Excellent, excellent. So the key is in using the comparison test is you have to find a series to compare your series to. So we look for, then when we do the comparison test, we look for series that we know something about. And a P series, we know under what conditions a P series converges or diverges. Okay? All right, let's look at the next example. The next example, we have the sum where n equals 1 to infinity of n squared over 3 minus 1 over 3n to the fourth plus 1. And again, just like with the first series, I think I can say this now. The first series, essentially what we did, we said, well, in the denominator, as n gets large, the 2n squared dominates. So essentially, I can, in a sense, ignore the 4n and the 3 in the denominator. I mean, I can't like ignore it, but as n gets large, the 4n and the 3 don't influence the result. So that allowed me to come up then with, okay, I'll use 5 over 2n squared to, you know, the series 5 over 2n squared as my comparison series. Well, for this second series, where n equals 1 to infinity of n squared minus 1 over 3n to the fourth plus 1, do the negative 1 and the 1, are they gonna matter as n gets large? Are they gonna? No, they're not. So what you can do is you can say, okay, let me just work then with n squared over 3n to the fourth. You see how I'm doing that? I'm doing this so it helps me. I'm showing you how to come up with the series, the comparison series. You know, what series am I going to compare my ugly series to? Okay, what nice series? This is how I come up with it. So in the solution, then, okay, I break down the inequality really in two steps. So I know that n squared minus 1 over 3n to the fourth plus 1 would be less than n squared over 3n to the fourth plus 1 because the numerator n squared is larger than n squared minus 1. But then on the other hand, you know, so now I have n squared over 3n to the fourth plus 1, but I want to have an easier series to compare with. So I recognize that the denominator 3n to the fourth plus 1 is larger than the denominator 3n to the fourth. So I can then say that n squared over 3n to the fourth plus 1 is less than n squared over 3n to the fourth. And that just reduces to 1 over 3n squared. So therefore, by the comparison test, well, our series has to converge because we're comparing it with a convergent p-series. All right, so I want to try to make this as simple as possible. Sometimes students, the comparisons, they get a little nervous about their, you know, doing a comparison test because they got to find, you know, they got to find a series to make the comparison. But it's not hard if you just, you know, think intuitively. But are there any questions about the comparison test? Are there any questions at all? Okay, I'm going to jump to the ebook real quick. Then I'm going to go right to the ebook. If may I do that? Does everybody have the solution down here? Okay, all right. Well, let me go ahead and go to the ebook. Once again, everybody has the solution copied all right? We're good? Okay, so let me see here. I want to go to the ebook. Chrome. And I want to show a comparison test, the formal test itself, the theorem. So let me see here. Testing by comparing. This is the comparison test right here. So if you have a convergent series, you have two series. If the larger series is convergent, then the smaller series is convergent. That's what part A says. Okay, if the larger series converges, then the smaller series converges. Now part B says if the larger series, no, in this case, if the smaller series diverges, then the larger series diverges. The reason I can tell which series is larger and smaller is the fact for B, the fact that the terms AN of the one series are larger than the terms BN for the other series. So therefore, the series BN would be the smaller series, and if it diverges, the series AN is also divergent. So this is how you use the comparison test. This is how you use it. And for the web-assigned homework for section 8.3, I think, well, the majority of those problems, they simply say, does the series converge or diverge? And you have one chance to get the answer right. It's either converge or diverge. And so you have to, be careful before you answer and apply the test appropriately. Okay, now while I'm at it, while I'm in the neck of the woods here, there's another series also, another test also, called the limit comparison test. This is another way to test for convergence or divergence of a series. So the limit comparison test, again, you're dealing with two series, and incidentally for section 8.3, all the series have positive terms, okay? So you don't have terms that are positive in the series and terms that are negative in the series for section 8.3. When you have a series where you have positive and negative terms, you have to use different approaches, and that's what we're going to talk about tomorrow with section 8.4. But for now, section 8.3, our series all have positive terms. So if you have two series and you were to study the ratio of the series, I'm sorry, if you have two series, two infinite series, and you were to study the ratio of the terms of the series as n goes to infinity, and the limit of the ratio of the terms of the two series equaled a constant, where the constant's a finite positive number, then either both series would converge or diverge. That's called the limit comparison test. Okay, and it's reasonable because what this statement means is that when n is large, the terms of the one series are going to be approximately that constant c times the terms of the other series. In other words, the terms of the one series are going to be approximately a multiple of the terms of the other series. Therefore, if the one series converges, the other series would have to converge. A multiple of a convergent series is a convergent series. If the one series diverges, the other series has to diverge. If you're a multiple of a divergent series, a multiple of infinity would be infinity. So that's the idea behind the limit comparison test. All right, are there any questions on that in general before we get to our next example? Okay, well, let's go to our next example here. Okay, so we want to determine whether the following series converge or diverge. All right, take a moment to copy it down. All right, so the first series, what does your intuition tell you? The series where n equals 1 to infinity of 1 over 2n minus 1. What does your intuition tell you? I mean, what does that series almost look like? What does that series almost look like? That's right, John. It almost looks like, that's right, Tyreek. Good, marvelous. And so, yes, geometric. So the series almost looks like this series, right? The series where n goes from 1 to infinity of 1 over 2n. And that's a geometric series. Is it a convergent geometric series? It is. We can rewrite it. Thank you, marvelous. Thank you, Robin. The common ratio is a half. But we have to be a little bit careful, okay? We have to be a little bit careful. Let me show you why. So let's go to this first solution here. So in this case, the terms of our series, which are 1 over 2n minus 1 over 2 to the nth power minus 1, those terms are going to be greater than 1 over 2 to the nth power. Because the denominator, 2 to the nth power minus 1, is smaller than 2 to the nth power. Indeed, we know that the series where n equals 1 to infinity of 1 over 2 to the nth power, we can write that as the series n equals 1 to infinity of a half to the nth power. That's a convergent geometric series, right? I'll add that in there. That's a convergent geometric series. where and the reason is the common ratio, a half, is less than 1, but it doesn't give formally information about our series that we're interested in, and it gives no information about the convergence or divergence of our series. Okay, I want to be a little bit careful. I mean, intuitively, if we had to root for whether our series converges or diverges, we would say yes, because it looks so much like that convergent geometric series. But if you try to use the comparison test, it won't work here. It won't work, because what you have, I mean, just to sort of show it in simple terms, you have here a convergent geometric series. We all agree on that. But that series, by virtue of the inequality up here, that series, the terms of that geometric series are all smaller than the terms of the series that I'm interested in, right? So this means then that the series that I'm interested in, the sum has to be larger than the sum of the geometric series. Well, sure, the geometric series, that sum is finite. It's a convergent geometric series. But the series I'm interested in, that sum could be finite, but it could also be infinity. How do I know? So you can't use the comparison test. We can't use the comparison test to prove if our series converges or diverges. In other words, the comparison test will not work here. Okay, does that make sense so far? So we're trying to be very formal in how we prove convergence or divergence of these series. Naturally, your fourth exam, this material is going to be on there, and when you show your work, you want to be, you have to justify if a series converges or diverges. All right, are there any questions so far on this? Are there any questions? Well, so what are we going to do? Well, since the comparison test didn't work, we could try the limit comparison test, because intuitively we still feel that our series converges. And the reason we feel that is because our series, when n is large, that -1 there doesn't influence the series. So our series really, we understand that our series behaves like a geometric series, like a convergent geometric series. We just have to formally prove that, okay? So we're going to use the limit comparison test. We're going to let a sub n be 1 over 2 to the nth power minus 1. And we're going to let b sub n be 1 over 2 to the nth power. Okay. Then we're going to look at the limit of the ratio of these two terms as n goes to infinity. Okay. I'll give you a moment to catch up here. I want to make sure everybody's comfortable. Okay, so what I'm doing is the limit of the ratio of the nth of the a sub n over b sub n. I want to rewrite. You know, I have the ratio. I have a complex fraction here in the first step. So I'm going to multiply the top and the bottom by 2 to the nth power. And this will give me the limit as n goes to infinity of 2 to the nth over 2 to the nth power minus 1. And then I'm going to divide. I'm going to multiply now top and the bottom by 1 over 2 to the nth power. And the reason I do that is so I can rewrite my limit so that it's more conclusive what the limit equals. The limit as n goes to infinity of 1 over 1 minus 1 over 2 to the nth power. We know that 1 over 2 to the nth power, as n gets large, goes to 0. And so this is going to equal 1 over 1 minus 0, which is 1. And that's the value of C in the limit comparison test. Okay, so far, are there any questions? All right, well, so what does this mean? This means that eventually, well, I'll move to the next page. But does everybody have this one copied okay? May I move to the next page? All right, well, what this means is that, thank you, Josiah, thank you. This means eventually that these two series are very similar because the terms of the series we're interested in will eventually be basically equal to the terms of that convergent geometric series there. So the fact that we have therefore our series n equals 1 to infinity of 1 over 2 to the n minus 1, that infinite series has to converge because the terms of that series eventually are going to be equivalent to the terms of the convergent geometric series. Basically, you're saying that the two series are going to be very similar as you take more and more terms, like maybe when you're out to the billionth term, the terms of, and you know, maybe trying to think intuitively here. Let's think millionth term. So, you know, the millionth term of both series, going from the millionth term, the million first term, the million second term, the million third term, and so forth. All those terms are going to be very similar to each other between the two series. And so the convergence of the one series implies the convergence of the other series. Does that make sense? Does that make reasonable sense? Or are there any questions on that? Thank you, John. I want to make sure I'm explaining it well. It's you know, I think if you intuitively have a feel for what's going on, you'll appreciate these different tests that you see in section 8.3. Are there any questions on that before I move on to the next we have part B. We have part B. All right. So that being said, let's move to part B. Okay. So So the series in part B is 1 plus a third plus a fifth plus a seventh plus a ninth, plus an 11th plus a 13th and so forth. What do you intuitively, what do you feel about this series? Do you think this series converges or diverges? And it's okay if you answer wrong. The terms of the series, are they approaching 0 for part B? Thank you. They are approaching 0. Does that mean the series converges then? If the terms of the series are approaching 0? Okay, good, Robin. It might converge. So Josiah, it might converge. It could converge, but doesn't mean it, like John says, it doesn't mean it has to, because remember the harmonic series. The harmonic series is this series. And that series, the harmonic series, diverges because the terms of the series don't go at a fast enough rate to 0. The terms of the series do get smaller and smaller. The terms of the series do approach 0 in a harmonic series, but they don't approach 0 at a fast enough rate. That series diverges. So this series here, I think, to help us understand the series, we need to get a formula for the series. So what would a formula for this series be? Obviously, it's going to be 1 over something, right? Okay, what would go in the denominator here? So I'm trying to get a formula for my series here. That sounds good. Very good, Robin. 1 over 2n minus 1. That's the formula for that series. Because when n is 1, you'll have 1 over 2 minus 1, and that's 1. When n is 2, you'll have 1 over 2 times 2 minus 1. That's 1 over 3. I mean, it checks out. So in this problem, okay, let me blow this up a little bit here. We first write down the series. And now I have to think of what test to use. The terms of the series are all positive, so we could use, well, the comparison test and the limit comparison test would both be applicable for this series. But I'm going to pick one test I'm going to pick one test over the other. Okay. So I'm looking at this series. Do you think this series would converge or diverge? So we're thinking in our minds here. Does that -1 there, as n gets large, does that -1 affect the sum? It does not. So in my mind now, I'm doing this in my mind. Thank you, John. I'm really looking at this series, the eventual behavior of the series, as the same as the behavior of the series where n equals 1 to infinity of 1 over 2n. Does that series converge or diverge? What do you think? The series n equals 1 to infinity of 1 over 2n. Okay, John thinks it converges. And it's okay to, speak your feelings. Sumaya thinks it diverges. Okay. All right, so we have a difference of opinion here from two smart people. Let me ask you this. Can I rewrite the series as some multiple of the harmonic series? Can I take this series here and write it as the multiple of this harmonic series right here? Keep in mind, 1 over 2 to the n is the same as 1/2 times 1 over n, right? I can write 1 over 2n as 1/2 times 1 over n. So what then goes in front of the harmonic series here? 1/2. That's right. Good, Robin. So let's discuss what we're doing here. I had a formula for my series. I recognize that when n is large, that -1 in the denominator doesn't influence the sum. Okay, so what matters? So essentially, that sum behaves like the sum where n equals 1 to infinity of 1 over 2n. But that series can be written as 1/2 times a harmonic series. So let me ask you now, do you feel our original series, 1 plus a third plus a fifth plus a seventh plus a 9 plus so forth, do you feel this series now converges or diverges? Let's see if we get a few more responses. Robin thinks diverges. right. Any other? John, what do you think? Do you think Tyrink thinks diverges? John, do you think maybe it diverges based on this reasoning? Good, and it does. It does. And this is the kind of reasoning I want you to do when in WebAssign, when you work on these Section 8.3 problems, where it only says, does it converge or diverge, and you have one chance to get the answer right. This is the kind of thinking I want you to be doing so that, you know, and thank you, Ryan, that's right. Before you answer the question, this is the kind of thinking I want you to be doing before you select your answer. So indeed, it does diverge. And to formally show it, we can use the limit comparison test. Now, I could try to use the comparison test, but you know, the limit comparison test is okay to use. I can use that. And the comparison test, I might run into the same problem that I had in the last problem, although maybe not. I'm just going to use the limit comparison test. So a sub n will be 1 over 2n minus 1. B sub n is 1 over n. And I'm going to look at the limit as n goes to infinity of the ratio of an over bn. And I rewrite that in a nice way. And you get a half. You get 1/2. Okay. Give you a chance to copy that. I want to make sure everybody's good. Okay, so the limit of an over bn is equal to a half. What does that half mean? What does that half mean? Well, what it means is this. The series that we're interested in, okay, hold on, let me clear that. The series that the series that we're interested in eventually behaves like 1/2 times the divergent harmonic series. That's what that means. Okay. The series that we're interested in eventually behaves like 1/2 times the harmonic series. And since the harmonic series diverges, you know, the series n equals 1 to infinity 1 over n diverges, so then must our series diverge. Okay? And that's how you work the problem. That's called, we've used the limit comparison test. Okay, are there any questions on that problem? Does everybody understand this? You'll be using the comparison tests and limit comparison tests quite frequently. in section 8.3. But there's another test we need to talk about called the integral test. That's also in section 8.3. And what I want to do is I want to go now to the ebook. All right, so I'm going to move on to the ebook here. All right, and let me see here, one moment. Yeah, this is fine. Okay, back into section 8.3. And let's see here. I want to just hold on here. They have a nice video on the integral test, but I want to just talk to you about like why. Well, let me show you what the integral test is. This is the integral test. It says, suppose you have a function that's continuous, positive, and decreasing over the interval from 1 to infinity. Okay? And if you let an be f sub n, then the series is convergent if and only if the corresponding improper integral is convergent. In other words, if the improper integral is convergent, then the series is convergent. If the improper integral is divergent, then the series is divergent. Okay. We've already the fact that a p integral, a p series will converge or diverge based on the fact that the p integral converges or diverges. That's an application of this. Okay, and what's going on here really is, I don't want to get like too technical, but you might wonder, well, how can we relate a series to an integral? You can do it because they have an example here of the series. This is going right near the beginning of the section. You have the series n equals 1 to infinity of 1 over n squared. Now we know that's a convergent p series with p equals 2. But if you were to integrate 1 over x squared dx from 1 to infinity, that improper integral is a convergent p integral that converges. But what they're doing is they're saying, look at the terms of the series. 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared. What they do is they draw a picture of 1 over x squared, and then using the right endpoint rule, they inscribe, if you remember from section 5.9, when you did the right endpoint rule, let me see, let me make sure I got the right section here. Yeah, that's when you did approximate integration and you were estimating integrals by using rectangles and adding up the rectangles. Well, if we choose for every interval, like 0 to 1, 1 to 2, 2 to 3, and so forth, if we choose the right endpoint to determine the heights of the boxes, the areas of each box, and the area of each box is going to be the same as the values in the series here. So, 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and so forth. Those are the values, those are the terms of the series, and they're the same as the areas of these boxes. Okay? Now, if you were to integrate 1 over x squared from 1 to infinity, don't worry about this first box. We'll add that area on later. Okay, that's finite area. But if you were to compute the integral from the integral of 1 over x squared from 1 to infinity, would that area be more or less than the sum of the areas of the boxes? That area be more or less? Who thinks they can offer an answer there? Let me see one moment. Let me get back to the, hold on. That's right, Tyreek. It would be more. It would be more. Very good. So that the fact that that's true means that, you know, if that greater area, and that's this area here, integral of 1 to infinity of 1 over x squared dx, and then you add the 1 to it, you know, that's equal to 2. You can show that equals 2. So that means then that's convergent. And so if the integral converges, the series converges, because the series, the terms of the series, which is the sum of the areas of those boxes, that area is going to be have to be less than 2. So this is just to give you an intuitive idea of how we can relate the sum of a series to the area of an improper integral, and that's how we get, you know, the integral test. And they do another example too, but we're fine. And by the way, the integral test, you don't have to start at 1. So when you go to the integral test, it's stated where the improper integral goes from 1 to infinity. But in fact, you could start your integral. It doesn't have to start at 1. It could start at 4 or 10. All that matters is that you have a decreasing, that the series decreases, and it decreases to 0. So where's an example where you would use the integral test? Okay, here's one where you want to determine whether this is example 1. You want to determine if this series, the series where n equals 1 to infinity of log of n over n, converges or diverges. So that series is a somewhat complicated series. You're not going to, I can't relate the term, the log of n over n, to any, I can't relate it to a P series. I can't relate it to a geometric series. The series is just not relatable to my favorite series that I know and love, geometric series, P series. It's not relatable. So I'm going to try to use the integral test. So what they do is they establish that this series is a decreasing series. You could plot the log of n over n and look at the sequence of the terms on your calculator and see that event, like for x greater than e, which is like 2.78, the terms of the series will start to decrease. That's all that matters. Eventually, the terms of the series decrease. So all you need to do is do the integral then from 1 to infinity of log of x over x. And that's a improper integral, right? So you write it as the limit as t goes to infinity, where your integral goes from 1 to t of log of x over x dx. You know, they just say, okay, that's the antiderivative. The antiderivative of this log of x squared over 2 used substitution, and they left some work out, but that's the antiderivative, and it equals infinity. So the fact that the improper integral diverges means that our series is also divergent by the integral test. Okay, so that's how you apply the integral test. Are there any questions on that? Any questions on that that particular example? So I'm not. It's in the book. I'm not expecting you to copy it, but. All right, so hopefully you're seeing math's a beautiful thing, with section 8.3. Now, I want to look at one more thing from section 8.3. I want to look at one more thing. And this deals with approximating a series. Approximating a series. So, again, I want to say this the right way. We have these series in section 8.3 where offhand we don't have formulas for the sum of the series. So if we approximate the sum of the series, it would be nice to know what the error is in our approximation. Okay, and that's a common thing. You saw that in section 5.9 when you approximated the integrals there, the definite integrals, using midpoint rule, trapezoidal rule, Simpson's rule. You had an idea based on the error bounds of, you know, what your error was or what it was less than. We want to have a similar experience here. So there is a theorem called the remainder estimate for the integral test. Okay, and I'm just going through here. Okay, estimating the sum of the series, that's right. That's where I want to be. So the remainder, R sub n. The remainder, R sub n, is the difference between the sum S. S stands for the exact sum of the series. That's what S stands for. The remainder is the difference between the exact sum of the series and the sum of the first n terms of the series, which is an approximation. So whenever you see R sub n, that's the remainder. That's equal to the difference between the true sum of the series and your approximation, S sub n, of the sum of the series. That's the partial sum, right? S sub n is your partial sum. Well, it turns out with the remainder test, it turns out that we can get an idea of the error, how large it is. And this is called the remainder estimate for the integral test. So the remainder, R sub n, is greater than or equal to the improper integral of n plus 1 to infinity of f of x dx. It's greater than that, but less than the integral where our limits are n to infinity of f of x dx. That's called the remainder estimate for the integral test. That's called the remainder estimate. And they intuitively, they develop why it's true in the book. But for our purposes, we're just going to, you can look at that, but we'll take it on faith right now. What's really important is the upper bound on the error. So the error, the remainder, you have a lower bound, which is this integral on the left in the remainder estimate, and then the upper integral, the integral on the right is the upper bound. What really is important, is the upper bound, because that tells us how large the error the error for our approximation could be. The upper bound, the integral from n to infinity of f of x dx, gives us an upper bound on our remainder or error of our series approximation based on n terms, adding n terms of the series. So on that note, let's go ahead and look at this last example. Okay, let's go ahead. And you can keep the theorem there in front of you if you want. But let's go to this last example. The book has a nice example on the remainder estimate, but I want to do one of my own here. I want to estimate the series where n equals 1 to infinity of 1 over n to the 4th power. That's a piece series. I want to estimate that correct to 2 decimal places. I'll let you copy that. One moment. Okay, so we want to estimate this series, and I know it's a convergence series because p is equal to 4. So, this sum does converge, and I want to figure out what the series, the sum is, correct to 2 decimal places. Okay, so to do this, we're going to use the remainder estimate for the integral test. All right, and if we look at the solution here, just blow this up a little bit here. By the remainder estimate for the integral test, the remainder, which is the error, I got to be careful here. The remainder, which is the difference, right? The remainder is the difference between the true sum S and the approximation of the true sum based on the first n terms of the series. That's the nth partial sum. The error in that approximation, the nth partial sum of the true sum, is less than or equal to the integral where the limits go from n to infinity of 1 over x to the 4th dx. See, in the problem, they say estimate the series correct to 2 decimal places. But in order to do that, I need to figure out how many terms of the series I need to be correct to 2 decimal places. So in order to find that, I need to compute this improper integral. Okay. So I'm going to compute it. So the remainder is less than or equal to the integral from n to infinity of 1 over x to the 4th dx. Okay, and I'm going to compute that. Naturally, I'm going to use the correct notation. Infinity, I'm going to replace that with t and look at this improper integral here equals the limit as t goes to infinity of the definite integral where n to t of x to the negative 4th dx. So please, please don't keep the limit. Don't remove the limit. Okay. It's very important in notation. Okay. How many are going to remember keeping the limits in their notation for the next time around here when they have improper integrals? How many are going to remember that in their work? Okay. Thank you, John. Thank you, Tyreek. It's good for you, proper notation. It's good for you. It's more work for me to study your notation and then, comment on it. It's more work for me. It takes longer to grade exams, for instance, when I do that, but it's important for you. Good notation will make you a better mathematician. Okay, so we will continue here. And there's just a side note here that this note to the right, well, let me just zoom out a little bit here. This note to the right about the function being continuous, positive, and decreasing on 1 to infinity, that means the integral test applies. So that goes without saying. All right, so the antiderivative of x to the -4th is x to the -3 over -3. And now I evaluate that improper integral, and I let t go to infinity. So 1 over t cubed this here goes to 0. And so this improper integral here, okay, will equal 1 over 3n cubed. That's its limit, 1 over 3n cubed. So far, are there any questions? All right. Well, remember what we're trying to do here. We are trying to, again, estimate our series correct to 2 decimal places. But in order to do that, I need to know how many terms of the series do I need to take. Is it 5 terms? Is it a million terms? How many? Okay. How many terms of the series do I need to get that accuracy? Well, I know that the error in my approximation is going to be less than or equal to 1 over 3n cubed. Since I want my approximation, my estimate of the series to be correct to 2 decimal places, this means then that I need 1 over 3n squared to be less than or equal to 5 over 10 cubed. Now, where's the 5 over 10 cubed come from? Because we said we want to estimate the series correct to 2 decimal places, that means that the error would need to be less than or equal to 0.005 in order to ensure that the series is correct to 2 decimal places. 0.005 is 5 over 10 cubed. If I had wanted the series to be correct to 3 decimal places, what would I need 1 over 3n cubed to be less than or equal to? If I wanted the series to be correct to 3 decimal places, what would I have here in place of 5 over 10 cubed? I would have what? Who can chat it out? And of course, I'll state the answer if no one's sure. correct to 3 decimal places would mean, okay, thank you, John. Very good. 5 over 10 to the 4th. That's what I would need. If I wanted correct to 5 decimal places, my remainder, I would want it to be less than 5. What did I say? 5 decimal places. I would want my remainder to be less than 5 over 10 to the 6th power. Okay. So, and the fact that you have this inequality here, you know, again, we're trying to find out what n is. Okay, how many terms do I need to go out in my series to get accurate enough approximation? That comes from the fact that the remainder is less than or equal to that improper integral, but if you set the improper integral less than 5 over 10 cubed, the remainder would be less than 5 over 10 cubed. I mean, if the improper integral is less than 5 over 10 cubed, then the remainder is less than 5 over 10 cubed. So now you have an inequality to solve. So 1 over 3n cubed is less than 5 over 10 cubed. If we multiply by 3n cubed both sides, we're going to get 1 is less than or equal to 15n cubed over 1,000. And note that the inequality doesn't switch because 3n cubed is a positive value. N is positive, right? Okay. So that means then 1,000 over 15 is less than or equal to n cubed. That's what that means. If you multiply both sides by the reciprocal 1,000 over 15, you'll be left with n cubed on the right alone. Okay, so when I'm just trying to take it slow, make sure everybody's comfortable. Okay, so 1,000 over 50. Are there any questions? Are there any questions? Oh yes, Josiah asked, where did the 5 come from? It has to do with the fact that if you, very good question, if you want to have accuracy within 2 decimal places, the third, the 5 over 10 cubed, which is the same as 0.005, having, why do you need the 5 there? It has to do with rounding. It has to do with rounding. That's really why it's there. It's the breakpoint that would ensure that your rounding were accurate to 2 decimal places. And it's always going to be a 5. Okay, always the 5's going to be on top. Okay, does that make sense, Josiah? Does that? Okay, thank you. Good question. Good question. Okay, well, so n cubed is greater than or equal to 1,000 over 15. What do we have to do to solve for n? What do we do to both sides of the inequality? I want to solve for n. I have n cubed is, okay, that's right, Josiah. Take the cube root of both sides. Okay, so I'll move to the next page if that's all right. And we're good? Okay, all right. Well, n cubed is greater than or equal to 1,000 over 15. Therefore, n is greater than or equal to the cube root of 1,000 over 15. And that means if you take the cube root of 1,015ths, you should get 4.058. Okay, 4.0548. And so you need 5 terms. See, n has to be an integer, right? So if mathematically n has to be greater than 4.0548, you would need to have 5 terms. And so this means then that our approximation of our sum, this is the sum, and we are approximating it now. So we have approximation signs. The sum is approximately equal to 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th plus 1 over 4 to the 4th plus 1 over 5 to the 4th. 5 terms. It's the 5th partial sum, and if you add that, you're going to get 1.080351929. And that'll be correct to 2 decimal places. And if you don't believe it, what you can do is you can compute the 6th partial sum. So the 6th partial sum would be where you add you have this you add another term. So the 6th partial sum would be the sum of the first 6 terms of the series, and you're going to get 1.081123534 for the 6th partial sum. But notice the two decimal places didn't change. They don't change. So you're adding more terms will not change the first 2 decimal places. So therefore, your sum of 1.080351929 is accurate to 2 decimal places. Okay, correct to 2 decimal places. And so if you're like, how many of you are in computer science majors here? Computer science majors normally need to take calculus 2. I think we have a few computer science majors here, because at office hours, I think 1 or 2 told me they were computer science majors. Maybe, does anybody want to give a thumbs up if they're computer science majors? You don't have to, but how many of you like computer science? Okay, Tyreek, I wish I knew how to code. So Tyreek likes computer science. He needs to learn, he wants to learn how to code. Well, of course, your college, Montgomery College or whatever college you're in, would have some programming courses. When you take, when you go to your higher level math courses, you normally will get into some programming as well as part of the course. But the thing is, you see, we know now how many terms that we need to take in order to get the accuracy we want. So you see, it's very important to know the number of terms, because that will determine how far out you need to run the program. You know, here we only needed 5 terms, but it might be, if you're doing like something with astronomy, astronomy calculations, since the planets are so far away, you might need to do, you know, a trillion, like 100 trillion terms or something to get you might need to take 100 trillion terms of the series to get the required accuracy. Because, you know, if you're with astronomy, if you're, off by just a little bit, it's a big deal, right? Remember, how many saw Apollo 13, that movie, where they had to be very accurate when they were coming in to the, Earth's atmosphere, and they couldn't be. It had to be in Apollo 13. They had to do it by sight, essentially. Get that accurate. They had to be accurate within a certain number of. Well, you'd have to see the movie, but how many recall that, where Tom Hanks is trying to estimate the level of descent? Okay, Josiah knows what I'm talking about. So, it's important to be very accurate sometimes, right? So, okay, let me stop there. Let me stop the recording. Are there any questions on this? How many think it's kind of cool? Okay, thank you, John. Thank you, Tyreek. Wonderful. Robin, thank you. That's great. That's great. Marvelous likes it too. Great.